Wayland dev version that you've recently compiled from Git. You got to do that a lot. Don't do that. You're making bonds.
I'm surprised I didn't get loaded as quickly as it did.
Oh, if I were to use the Windows machine that is on the instructor workstation, I'll still be waiting to sign in.
Yeah, so I'm pretty sure the world would collapse on itself.
Imploding. It's called implosion.
Exactly.
All right, so we're back. So we just have to the ROM. Unfortunately, the ROM file is gone because it's in the temp folder. But that's okay. We can just re-download it from the assembler. So the assembler, because it's a cloud-based document, it's still here. So the RAM file is still here. We just have to re-download it. No biggie. So download as CSV. Name it as test again. Go back to the simulator. Oops, not save. Load. And then we want to get it from here. All right, so we got our program back. Now it's time to single clock it again until we get to 630. So this time we're just gonna keep going until we get to 430 as the ROM location. We should be there now. There we go. So you can see the content is correct. Okay, it kept the change because we saved the file again, which also means if you want to update your setup, you just have to re-download the file from the Google Drive again. That file is already updated. Cool. So now the question is it going to do the right thing? And you can see that it is already addressing the correct byte. So I know for sure that it's going to do the right thing because this is the byte that contains the address of where we need to go. Before I fixed it, it was using one of the registers, I think it's register A, to specify the address, and that's why it went all the way to location FF, which had a default value of 0, and that's why the next location it will go to is location 0. But now it is going to location 08. Okay, so it doesn't hurt to single step a few more times just to double check. Okay, so we want to look at the program counter to update from 06 to 08. So Control T, and you can see how it's updated to 08. So that means the halt instruction we're going to be stuck at is the one that is at location 8. And you can see how now the PC is 09. It is not going to move anymore because we are already at a halt instruction. So we fixed the problem by analyzing, okay, this is not supposed to happen, and we go back to the ROM, locate the correct bit to change in this case, fix it, verify the change, and make sure that it's all working now. Is that okay? So I got one more place to fix, okay? In addition to this, I got one more place to fix. I do not intend to really introduce that in this class, but since we're here, we might as well, introduce the whole thing. So as they say, we'll cross, what is it saying? When we get to the bridge, we'll cross it or something like that? Yeah. Okay, so my saying is, when we are on the bridge, might as well we go fishing, right? Perfect spot, go fishing. Don't just cross the bridge, enjoy the trip. Bring your fishing gear. Okay, so there's a zip file that I talked about earlier in this class. I'm not sure whether I really show you guys what it is and what to do with it. So I'm going to show you guys what to do with it now because this is how I generate all the ROM code, all the microcode slices. So we'll go ahead and download this entire zip file. And we can put it into the temp folder because I'm going to unzip it into the processor subfolder. So now we switch back to here and open a new tab. And then we go to cisp310. And I misspelled processor. It spells processor. So we'll change that first. Okay. And then we'll go ahead and unzip the file from the temp folder called opcodes.zip. It creates its own subfolder called opcodes. And I think we talked about it slightly in this class. there's one file corresponding to each mnemonic that the assembler can recognize. So that means each executable of that name generates just that single opcode. So if I were to run JSI, okay, /JSI, it's waiting for the input file, but the output is like that. Do you guys, oh, it is correct. It is correct. So that means somehow I forgot to use the output of this thing to update the actual ROM file. So something did not go as expected. Okay, so we just do a make, all.rom is up to date, copy all.rom to the parent folder, but everything is fixed already. If you just re-download processor wdpc2.circ into your own folder, that one is fixed already. But if you look at jsi.c, this is basically what I need to use in order to make sure that to generate the opcodes, because I'm not going to count individual bits when I have so many variants of opcodes to deal with. So instead, I use a structure to deal with this, and I just have to look up which entry here is corresponding to I think it's the address mux, and make sure that one is a 1. I believe it is this guy here. I could be wrong. So are there any questions about this part here? If you're curious, okay, go ahead and check it out. Otherwise, I'm not intending to have any homework assignments involving this for this class. Is that okay? Cool. All right. So we are going to talk about conditional branch. We have already talked about conditional branches. We talked about the compare operation. So we are done with most of the instructions that are responsible for the control structure of a program, which means from our module perspective, we are now ready to move on to talk about how to compile a program by hand. Okay? I cannot remember which student. I think it's a previous student of mine, and that person was taking a compiler class at Sac State, and that's a fun class. Especially once you have taken assembly language programming, then you actually get to understand the whole process. So this is the module, the new module that we're going to get into. It's how to compile control structures in a high-level programming language into assembly code. In other words, at the very end of this semester, I want you guys to be able to look at a simple C subroutine and be able to convert the entire subroutine into assembly code. Okay? So you will become the organic compiler. Okay? All right, so this module is kind of interesting because every single section starts with a typical, correct, and structured C control structure. So right here, C is just a condition. C can be a very complex condition, can be very simple. It doesn't really matter. It's just a placeholder. Block 1 and block 2 are also just placeholders. Okay, so block 1 can be really long, huge. Block 2 can be the same way. It can be empty too. Okay, there may be nothing in block 2, which degenerates this conditional statement to just an if statement without the else portion. The second version is a flattened version of the same code. In other words, this is not structured anymore. But the question is, does it get the same thing done compared to the earlier structured version? That is the question. So when you look at the structured version, you will execute block 1 if and only if the condition C is true. You will execute block 2 if and only if the condition C is false. That is the behavior of that code. And then depending on which, independent to which branch, after block 1, you continue execution at the end of the conditional statement. After block 2, you also continue execution at the end of the conditional statement. That's the behavior of a conditional statement that we know of in just about any high-level programming languages. It doesn't matter whether it's C, C++, Java, or Visual Basic, they all basically behave the same way. So now when we look at the flattened version, the question is, does it get the same thing done? It looks weird, but does it get the same thing done? So do we execute block 1 if and only if the condition C is true? Do we execute block 2 if and only if the condition C is false? Do we continue execution past the end of this construct after each of the blocks? So after block 1, we go straight to the end of the conditional statement. After block 2, we also continue execution at the end of the conditional statement. What do you think? I think it gets the job done. Okay. Are there any questions about the definition of labels, like this construct here, or the statement called goTo, like that one here? Are there any questions about those two? Yep. Okay, so a goTo is basically an unconditional branch. It will continue execution at whatever the label is indicating. And then label with a colon right after it is the definition of a label, which is the same as the assembly syntax. So in this case, if the condition C is false, which means the negation of that is true, then we will continue execution at label L1, which is down here. So that means if C is in fact false, we will execute block 2. On the other hand, if C is true, not C is going to be false. So the statement go to L1 is not going to execute. This if has no else, which means it will just kind of fall through to block 1. After block 1 executes, we will use this goTo to unconditionally go to label L2, which basically just continues execution after this entire chunk of code. Yes?
If you have something after L2,
Yep.
so like you have not, and then you go to L1, will it then run not after running BLK2?
Say that one more time.
Okay, so under label L2, if you have not, which does nothing,
Right.
and you go to L1.
Who goes to L1?
So if not C, and then it goes to L1, will it run BLK2 and then not? Like basically
It will
doesn't
run.
stop.
It will fall through.
Yeah.
So that means that whatever instruction here you have, after block 2, it will automatically run that.
Okay.
Which is also the same as the behavior in your assembly code.
Right.
Yep. That is correct. So any other questions about this code? The equivalency between the structure code, which has curly braces, and the flattened version, which has no curly braces. No questions? This is all good? All right. So the second one is basically the simplified conditional statement that has no else statement. So in this case, the structure version is just if C block 1, and then the flattened version is if not C go to L1, and then the block 1. Okay, because there's no else statement, so there's no need to specify block 2 because there's no block 2. Okay, is that okay so far? Okay, all right. So the next control structure that we want to talk about is a while loop. So a while loop in C looks like this. Okay, it has a while keyword, a condition in parentheses, and then you have a block of code, a statement block that you want to execute, as many times as it takes in order for C to become false. Okay, so is that okay? And this construct exists in almost every high-level programming language as well. So now the question is the flattened version doing exactly the same thing? We have a label L1 defined at the very beginning of the entire chunk of code. And then we have a conditional statement that says if not C, okay, if the condition to stay in the loop is not true, then we go to L2. L2 is a continuation label. It continues execution with whatever is after the while loop itself. If C is false, if C is true, if C is true, then not C is false, that means it's not going to go to L2. If it doesn't go to L2, it's going to continue with block 1, and then block 1 executes, and then it has an unconditional branch, go to L1, to go back to L1, and then we reevaluate the condition C to see if it is time to go to L2 again. So that behaves the same way as a regular while loop. It is just that now it is flattened. There are no curly braces anymore. Yes?
Should there not be a semicolon after the first L2? It's supposed to be.
The first L2, yep, it should be a semicolon and not a single colon. You're correct. Let me fix that. Let me see if my home computer is up. Yep, okay. Do you guys remember the module number?
303.
303, okay. So instead of naming my modules, I just use a sequential number. That makes it so much easier. And we're looking for go to L2 with a colon. Okay, so we're looking for go to L2 with a colon. There we go. Change that to a semicolon. And then we can republish the whole thing. There we go. And then refresh. Let's see, is it updated? Yep. Thank you. You'll make a very good compiler. Good job. I meant it as a compliment. It's just like when people say that tech, you're gonna fail the Turing test. I go like, well, thank you. Why would I want to pass the Turing test? That would be irrational. Okay, so post-checking loops, a do-while loop, which does not occur very often. When was the last time you had a do-while loop or repeat until loop? A while ago, right? Because usually we do not use a do-while loop. The only time a do-while loop makes sense is block 1 is necessary to generate the condition C so that you have to perform block 1, then you check the condition. Okay? But most of the logic that we need in algorithms are exactly the opposite. We check the condition first, and then we decide whether to do something about the condition or not. As opposed to we perform some operation that will set a condition to be tested. Okay? So this does not occur very often, but if it does occur, okay, the equivalent code that is not structured looks like this. We have a label L1 once again because it's a loop. You must have a label early at the end in order to branch it back. But this time we have block 1 first, and then we say if C, if the condition to stay in the loop is true, then we go back to L1. So this one turns out to be simpler compared to a while loop. All right, so do we have any questions about these 3 control structures in C and C++ and how we convert or flatten these structured code so to make use of a conditional go-to statement, basically? Yes?
For the while case, it's basically just following through until not C happens and then it jumps out and is what's going on, right?
That is correct. So that means, even for the do while loop?
For the while.
For the while? Okay, so for the while loop, okay, I'll show both versions. So as long as C is true, not C is going to be false. So if not C is false, then we are not going to execute the then statement of this particular if. So it's not going to go to L2. It has to fall through to whatever is next to the conditional statement, which is the body of the loop itself, block 1. At the end of block 1, we have an unconditional branch back to L1, which basically do the whole thing again. So yes. It looks kind of awkward because we have to negate the condition, but that's only because it makes more sense to look for the exit condition and then have a branch to the exit label as opposed to looking for the true condition or the state in loop condition to branch to the body of the loop and then have a branch to get out of the loop. Yep, question? Oh, okay. Because you flagged your neon color marker. So. Any other questions? No questions? What if we have a loop inside conditional statement that is also inside a loop, which is inside another conditional statement?
One more time.
What if we have a loop inside a conditional statement that is inside a loop inside another conditional statement? It's all nested. Okay? That's structured programming. So what do? You just have to unravel it one level at a time. The same technique, just do not use the same labels again. That's the most important part, okay? So you have to be kind of more structured. This is just for demonstration, so that's why I use simple label names like L1, L2, L3. But when you're actually doing this inside a complex program, you probably want to come up with a systematic way to come up with a label name. So that way, just by looking at the label name, you know which construct it belongs to. Okay, so I have some suggestions later on, but they tend to be pretty mechanical, so I'm not sure whether you guys want to use that or not. All right, so are there any questions about converting control structures into the flattening control structures? Yeah, go ahead.
Is there one for if?
Huh?
If, like, how is if done?
You're looking at it. What about for? The for loop in C and C++? What about that? Well, the for loop is nothing more than a while loop with the initialization spelled out, right? With the post operation also spelled out inside the parentheses. So, whatever works for a while loop is going to work with a for loop as well. You just have to move things around a little bit to make it look like a while loop. What about a switch statement? Well, a switch statement is kind of a special case because it's not exactly like an if then else because of if you forget to break in a switch statement, it falls through, which I absolutely hate. That doesn't make sense either. Yep.
Could you just put in each of like have a bunch of ifs down the line and then have a break up to the same point?
Yep, you can do that. So the break converts to an unconditional branch to the end of the whole thing. But if you don't see a break, then you just basically have landing points for all the labels, and then you have a whole bunch of conditional compares to see which one it needs to go. So, but that's basically we can do it with a conditional statement as well. So that's why we are not going to talk about the switch statement. Okay, so the next question is, what about this condition here? It can be a very complex instruction, a complex expression. In other words, even after we flatten the control structure itself, the condition itself can be an expression that is an overall disjunction, that has components that are conjunctions, and then inside we have negations, the negation of disjunctions, la 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 la. So what do we do with a complex Boolean expression as our condition? That becomes the next question. Well, as it turns out, we have very systematic and mechanical ways to deal with that as well. If the condition is a negation of something, you can always convert and do it this way. In other words, if you want to go to L1 if and only if the condition is false, then you can say, oh, if the condition is true, we go to L2, which is a continuation label, and then if you do not go to L2, then we have an unconditional branch to L1, which ends up going to label L1 if and only if C is false, but it makes the code a little bit longer. But the bottom line is, go-tos we know how to deal with, right? Because they're just unconditional branches, JMPI instructions. That's easy for us to deal with. What we want to get rid of are these operators, which do not exist in assembly language. So the objective is to get rid of Boolean operators at the expense of complicating the go-to, the labels, and stuff like that. Is that okay? Let's move on. What if the condition is an OR? The top operator is an OR. What do we do with that? So in this case, obviously, in the original code, if condition C is true, we don't even bother to look at condition D. We just go to label L1. Yes?
I was just wondering, since we already know how to do math to convert the conditional statements, could we just do the math operations before we do the conditional statements and go-to instead of doing the additional go-tos?
In some cases, yes. But if C and D in this case are complex, then you still have to boil it down to comparisons. Do you see what I mean? Because in this case, C can be a conjunction on its own, or the negation of conjunction. So that means C takes a little bit of work to break it down as well, and D can be the same way. So we are basically systematically removing Boolean operators by making the control structure itself more complicated. But the expressions get simpler because now we got rid of disjunction. Okay. So are we buying this? Are we basically saying, if C or D go to label L1 is really the same thing as saying if C go to L1, if D also go to L1? Is that okay? Is that preserving the short-circuited evaluation nature of Boolean operator evaluation? Yep. Okay. Because if C is true, we don't even bother to evaluate D, which is exactly what C would behave. Okay. And the last one is conjunction, which is actually a little bit awkward because conjunction goes like this. If the original one is if C and D go to L1, then the flattened code, which gets rid of the operator and, is going to be if not C go to L2. In other words, if the first condition is false to begin with, don't bother with the second one, just continue execution. On the other hand, if we are not going to L2, which means C is true, then we check the second condition D. Because by the time we check if D, that means C is already true. So if D is also true, that means C and D are both true, and that's when we go to label L1 to preserve the meaning of the original statement. So is that okay? Is 4.3 okay? Cool. All right. But sometimes we don't have to do that. Okay. So sometimes we can say, if you have a negation of a comparison, then you can just kind of flip the comparison itself. So instead of looking at this as the negation of x is greater than or equal to y, you can just say, oh, okay, that's just really the same thing as x is less than y. Or if you have something like this, which looks kind of complicated because it's an OR statement or it's an OR operator, but what it really means in this case is x is different from y. So you can just say, oh, okay, so we are branching if and only if x is different from y. So there are certain cases where you can just simplify the expression in a comparison instead of applying those techniques that we talked about earlier. So do whatever makes sense, right? So if we are boiling down to comparisons already, and you look at all the conditional branch instructions and go like, oh, we can do this already just by changing the expression or the comparison itself, then go ahead and do it. So are we doing okay so far with all this? Okay. We move on to comparison. So this is something that we talked about already. The only comparison that we really need is less than, because you can express less than. This is the original expression, and then this is basically the same meaning, but without using any operator other than less than. So if x is greater than y, it's the same thing as y is less than x. X is less than or equal to y is x is less than y or x equals y. Now, why do you think I broke it up into something like this instead of not x is greater than y? Because we can check for equality. Which flag after a comparison indicates equality? The Z flag. Very good. So we have the B or the L flag to indicate less than, and then we have the Z flag to indicate equal to. So we just want to boil every comparison operation down to just those two operators that we can deal with. Okay. So the next one is greater than or equal to. We just change the order of the operands. That's it. X equals y is easy. We just check the Z flag, so it is natively doable. X does not equal to y is the negation of x equals y, which means we branch around when it is equal to, and then when it is not equal to, that's when we perform the next operation, which is an unconditional branch. Okay, so what do you say about an example now? That sounds good, or Okay, so let's go ahead and do that. So we'll use the text editor and come up with some C code with a. Okay, so what is going to be a complex expression that you guys want to break down into those operations? So we can assume that we only do things with the registers. So we have A, B, C, D, and you guys can come up with some kind of awkward Boolean expression.
A and D are equal
Okay, so A and D are equal to B, right? So that boils down to A equals B or D equals B, right? Did I hear you correctly or did I misunderstood? Did I misunderstand you? You want the and? Okay. All right, so let's do this. Okay. And we'll even give it a block of code. Okay, what about we just increment C over here? Okay, so we'll convert this into assembly code. So the first thing we do is we flatten the conditional statement, which means we say if, and then we say not. Okay, and I can do this, copy and paste, right? There we go. And I don't need the curly braces anymore because now I can say go to label L1. And I'm just going to change the name to endif as a label because that makes a lot more sense. So endif is going to be defined here. And then we define the body over here. So plus C is going to be here. Is that okay? This is the first step. Now, after the first step, it is still C code. This C code actually compiles. So that means during the flattening process, you can actually test your code in a C debugging environment to make sure that your flattening process is okay. All right, so we look at this and go like, we have a pretty complex, well, I wouldn't say pretty complex, but we have a complex Boolean operation here, and no one single comparison followed by conditional branching can do this in assembly. So we have to kind of simplify this a little bit. This one is kind of special because at this point we can use De Morgan's law too, because we have a negation of a conjunction. So if you want to use De Morgan's law, go ahead. If you want to just follow the mechanical way of doing things, that's okay too. So it's up to you to decide, how you want to do this. So what do you guys want? Do you want to use De Morgan's law, or do you just want to mechanically follow those rules?
Let's use De Morgan's law.
Use De Morgan's law. We can do it either way. We can do both ways. Okay. So let's first use a De Morgan's law. So I'm going to denote here. Okay, De Morgan's law. Okay. So in this case, De Morgan's law is the negation of A and B. A and B being some Boolean operations, Boolean values. It's really the same thing as not A by itself or not B by itself, like that. So that's De Morgan's law. So after the application of De Morgan's law, so we will restate this as A. Okay, so I'll go step by step. Not A equals B, or not D equals B. I'm just counting parentheses now, making sure, okay, that looks right to me. Plus C, and then end if. Is that okay? Okay. So now we, instead of having a negation on the outside, we now have negation applied to each individual term, and a disjunction, and then another negation to the other interior term, which seems like we're making things worse. But the negation of A equals to is really A does not equal to. So we can now simplify that to just if A does not equal to B, or D does not equal to B, then we increment the counter C. And if. Is that okay? So there's nothing we can do at this point to simplify this any further. So now it's time to actually take out the disjunction, which means we now translate this to if A does not equal to B, go to the label, let's see, nope, somewhere along the line I forgot about the go to and if. There we go. There we go. I forgot about that. Sorry. So now we have that label, which is go to and if.
Oh, I thought you intentionally left them out.
Oh no, I forgot. If D does not equal to B, also go to and if. Otherwise, we increment C, and if is still defined at the same spot. So now the question is this code still doing the same thing as the original code? The original code says if A is the same as B and D is the same as B, then we go ahead and increment B. This code is saying if A does not equal to B, don't even bother to check anything else, just skip the rest, okay? On the other hand, if A does equal to B, but D does not equal to B, also go back to skip the increment. So the only time we get to plus C is when this condition is false. But if A does not equal to B is false, it means A equals B. But we also need this one to be false, not to branch around the increment of C. So that means if D does not equal to B also has to be false, which means D has to equal to B. So that means by the time we get to plus C, A has to equal to B, D has to equal to B, which has the same meaning as the original code. But now we can try to convert it into assembly code, because it is simple enough, because every single condition is now a single comparison. So now we can actually do something and say, okay, can we convert it into assembly code now? So the assembly code is compare AB, okay? We cannot avoid this one, we have to do a compare first. But because the toy processor does not have the negated test, in other words, it cannot branch if and only if the Z flag is a 0. It only knows that we only have a conditional statement that says if the Z flag is a 1, then go ahead and branch. So that complicates things a little bit, because now we can only use JCI. But the JCI is going to be going to another label. So we'll say check D, okay? So if A does equal to B, then we check D. Otherwise, we do an unconditional branch to end if. Check D is over here. Okay, so now we do the other compare, which is CMP_DB, JCI to increment C, and I usually do it like this. I define the label right away so that I don't forget to do it later. And if not, we skip over the whole thing. So we do a JMPI to end if. So by the time we get to increment C, we just go ahead and increment C. And then we have the end if label at the end here. So are there any questions about this code? In other words, we look at the completely flattened C code, which is this portion, and then we translate that into the assembly code with a toy processor. Yep.
If you have more than A, B, C, and D, you would have to like take things in and out of memory.
Yeah.
Registers in this process.
Yep. So you have to get things in and out of the registers. Yep. Yep. Go ahead.
What was
JCI is jump if and only if the Z flag is a 1. But if the Z flag is a 1, that means in the comparison, the two things that you're comparing are the same. So are we okay so far with all this stuff? So, but you can see how it is kind of a mechanical process. Okay. Because if you want to take the flattening to the next level, you can basically just look at this and go like, I don't like negation because we only have JCI. So you can, at this point, you can say, okay, if A does equal to B, go to check D. And then check D is going to be defined here. If not, you go to end if. Like so, and then if D equals to B, then you want to go to increment C. Otherwise, you go to and if. Increment C is over here, plus C, and if. In other words, this is the flattened C version, okay, of this code here.
No compile in C.
It will compile. Yes. It's all syntactically correct in C. Now don't do this with your homework assignment with Professor Fox or subsidiary. Write a program to systematically go through your well-formatted structure code to flatten it to like this, right? And then turn that in. Yep.
After you increment the C, do you not need a semicolon there?
Oh, yeah. You'll make an excellent organic compiler as well. Good job. Yep.
Maybe I forgot the original conditional statement, but isn't that code that you just wrote more like an and rather than a or?
No, it's an and. Okay, so what I did was I look at this thing here, and I go like, it has a negation that I do not like, because if you look at this, okay, let me write this in a different way so that you can say, oh, okay, so it's the same thing as that, right?
Okay. Do you mind just going back up to the original conditional statement? Maybe I forgot what it looked like.
Okay, sure. So if I go back to,
I think it was at the top of the.
okay, so you want to look at the actual conditional statement?
No, I'm sorry.
It's like when we started.
Oh, the example itself. Okay.
Oh, okay. Well, never mind.
Okay. Yeah, so the original one is an and, but the focus of the bottom portion is not dealing with the and, but dealing with the negation. So this dealing with the negation, this chunk of code, is now translated into this chunk of code. Is that okay? All right. So it really is just a mechanical process, where you have to do it like really step by step. But the cool thing is, all the way down to this version of the flattened version of the original code, this is still C code. It will still compile. If you did not make a mistake in the process of flattening up to this point, your program would actually behave exactly the same as before. So all the same test cases they can throw at your program will still work exactly the same way as before. Yep.
So is everything in assembly then considered, if it's the block of code, is it all considered to be under main and it just goes from the top down?
There's no such thing as main in assembly code. We simply start execution at location 0, 0 in RAM. That's it.
Oh, okay. So there's no methods then?
There's no main, there are no subroutines
Oh, okay.
in assembly.
Okay. Gotcha. Because that was my question. If there is a subroutine, then how would it, after calling it, how would it know how to return back to the correct
The
spot?
concept of a subroutine is a high-level concept, which is an illusion from the perspective of assembly language programming.
In assembly language, is it just actually chunked again when it comes to that subroutine call? As it?
That's another bridge that we're gonna cross. Okay, so since you mentioned that, I can point out where it is. So right here, calling and returning from subroutines, which is the next major module, that will talk about how to deal with subroutines in assembly. But for now, we are much more concerned about the control structure itself, and not so much about calling and returning from subroutines. So are we okay so far with flattening a program? It really is just a step-by-step process. The only thing that you have to be really careful about is how you name your labels. Because if you use label L1, L2, and L3, that sort of labels, sooner or later you will forget which label has been used already, and then you accidentally use a label that has been defined earlier, then your program will go really wrong, because it's going to go to a label that it's not supposed to. So that's the only part that is kind of difficult to deal with. Yep. Scroll down a little bit. So we have the C code up here, and then the assembly code down here. So there's really no other way to convert this into. There's no other way to simplify to do it in C anymore, because in C, A equals B is kind of like an atomic expression. You cannot break it down any further. But in assembly, you have to break it down into two separate steps, which is going through the comparison, which is basically a subtraction that does not store the result, and then you have to examine which flag you want to look at, and then do a branch according to that flag. So there's no way to do it to do the equivalent of this in C anymore. So this is the last step. This is the very last step that you can still test using a C compiler and a C debugging environment. But that takes you a long way, because from here to here is a very, very mechanical process. If you name your labels right to begin with, this conversion process does not involve any new labels. You're only breaking a comparison operator in C into a compare followed by a conditional branch. And that's a very, very mechanical process. And the chances of you making a mistake in that particular step is very low. The biggest chance of making a mistake is actually converting all the way down to this particular one, because if you use a wrong label name or you branch to the wrong label, then your code is not going to work the same way as the original code. But this is still testable in the C environment. You can still use code blocks to test this. Is that okay? Yep.
So when we make our own programs in assembly, would you recommend just writing it in like a structured language first and then converting it?
Absolutely. So you can use C and C++. It doesn't really matter. You can use pseudocode because we are not actually using a compiler. You're not writing a compiler in this class. So you can just use any type of pseudocode that has the same features that we have talked about, and then do the conversion step by step. We're not going to do very complex algorithms in this class because after all, your processor only has 256 locations. And some instructions take up 2 locations already. So that means you can not really write very complex programs in this processor. But it will still be fun. I mean, you can still write enough code to be, you can still write enough code for the toy processor to be educational. Is that okay? And then somebody's going to say, well, there are no commercial processors that only has 256 possible programmable locations for instructions.
Not anymore. But it's
Hmm?
not anymore, right?
Not anymore? Not anymore by how many years? Okay, so there's a whole family of processors called the AT-Tiny. And let me go here. Okay, this is something that some of you may actually be interested in. Nope, not DigiKey. DigiKey, D-I-G-I-K-E-Y. Okay, there we go. So DigiKey is an online merchant, but they sell components in electronics. You can order 1, 2, parts if you want, but you can also order up to like hundreds of thousands if you want. Okay, so they go by they would cut a tape with only 2 resistors on it, or you can just buy a whole reel of tape of those things, so you can put it onto a what we call a pick and place machine, so you can automate the whole process of putting components onto a PCB on the printed circuit board, and then the whole circuit board with all the components already on it would go through what we call a reflow oven, and then you will heat up the solder paste, and then parts actually get soldered. So that's how we make circuit boards in the manufacturing environment. But what I want to do here is to look up AT-Tiny as a part number. So we want to look at things that are in stock, okay? And we want to look. Okay, let's go to. Okay, embedded processors. This is one really cool feature of DigiKey, is it allows you to do parameterized search. And these are not, so in other words, you're not looking for keywords. You're looking at actual characteristic of the parts, which is really great. So we can, let's see here. So we want to look for cut tape because that means you can buy like 1 or 2 of the components. Okay, Okay, and we want to look for things that are actually in stock. And then we narrow it down to 1.2 megahertz or 4 megahertz. And then we want to look at the operating voltage. So you can see that the operating voltage goes from 1.8 volts to 5.5 volts. So that means you can use a single lithium-ion cell to power up these parts, which is great because one single cell can power up the processor. And you can also see right here, program size is 512 byte locations. Each location has 16 bits. So I lied, it is not quite as bad as we thought it would be. It is actually 200 and how many locations again? 512, right? Yeah, so 512 locations for opcode. So that's quite a lot. Yep. They used to make parts that are actually smaller, but not anymore. But this is the reason. If you look at the price, this is the reason why you might still want to know how to write assembly program on a tiny little processor part, because the price each is 60 cents. This is if you buy one. You can say, I want to buy one, 60 cents, but they will charge you $16 for shipping. Okay, so what if you want to buy more? How much do I pay if I want to buy more? Okay, let me go back and look at the part number first. So the part number is ATtiny12. Okay, so we'll look up ATtiny12. And this time we'll look for, okay, so this is okay. I don't have to break it down any further. And we can look into this. We are looking at the price now. Some are discontinued, so they don't reflect the price. Oh. Okay, there's a second page. It doesn't tell the unit price because most of these parts are obsolete. Okay, what if I just look for ATtiny? Go to microcontrollers, and then we look for things that are in stock, and then we'll sort by price, right? So 29 cents for one part here, and we can sort by price too. 17 cents for this particular part, but you have to buy how many at the same time? Minimum quantity is just one. Yep, if you buy one, it's 18 cents. How much do they charge you for parking on a per day basis here? Is it $2 now? $2, right? So you can buy 10 of these things. But think about the application. These things are easy to work with because you can. It doesn't need any external parts. You give it, a zero. You give it the voltage, from 1.8 to 5.5 volts. It has the internal oscillator. It just runs. So minimally, what you need to run these things is really just a battery and the part. Okay, and when you look up the part number here, okay, so let's look at the part number, which should give you a link to the data sheet. So where's the data sheet? It's the ATtiny5. What I am trying to do is to show you the reason why this is actually important. ATtiny5 data sheet. Okay. And we'll look this up. And data sheet is right here. Click on it. Okay. And complete data sheet summaries. Summary is good enough. Because what we're looking at is the power consumption. And so let's look at the power consumption right here. So here's the power consumption of this particular chip. Okay, how many people have taken a physics class? Okay, so you understand that power dissipation is the product of current and voltage. Okay? So these things can run at 1.8 volts, which is pretty low. Unfortunately, it's not low enough to have one single alkaline cell or one rechargeable metal hydride cell to power up one of these things. But a lithium-ion battery, which is 3.7 volts, is definitely more than enough to run it. And then you multiply that by the current. This is 200 microamp. So 1 microamp is 1 millionth of an ampere. Okay? So now the question is, if I have a cell phone battery, okay, let's say it's 3.7 volts at 3,000 milliamp hour. Okay, I think these days 3,000 milliamp hour is not even considered, you know, it's about average.
Yeah, exactly.
Yeah. So let's see how long it can run when it's in active mode. So we're not even counting idle mode or power down. Okay? So we are saying that we are running this thing at 1 megahertz the whole time. So we'll go through some calculations. So how am I going to do some calculations here? I know. We'll go to Google Drive and use a spreadsheet. That's how I end up with a lot of untitled spreadsheets. So, but spreadsheets are great. They're really, really great. So we say, okay, come on. Okay, so we have current draw, and it is 200 micro, right?
Yeah.
So it's 200 E minus 6. Getting back to the floating point or scientific notation, right? Because it's 200 times 10 to the power of negative 6. So that's our power consumption. The voltage is 1.8 volts. We'll just say 1.8. And then over here we'll say battery capacity. So we are measuring everything in ampere. So this time we'll specify 3, but it is 3 amp hours. So now the question is, do you want to count by hour or do you want to count by seconds? Because if you want to count by seconds, you have to multiply this 3 by 3600, which is the number of seconds in an hour. But let's say we just want to count in hours. Trust me, hour is fine. Okay. So now the question is the duration. How long can this battery, which has 3 amp hours, to power up this particular processor continuously in active mode? So that becomes 3, this number, divided by the current draw of the chip. It can run this many hours. You look at this and go like, okay, fine. How many days are we talking about? Okay, so we say duration in days. This is going to be this number divided by the number of hours in a day, which is 24. So this is basically 625 days. Close to, I guess we can count it as close to 2 years. 1 year and 1 3/3 of a year. That's from one single lithium-ion battery that is just a standard one on the cell phone. And this processor can run at full speed, active mode for 1.5 years. And then you guys would go like, but what can this possibly do? This is kind of useless, okay? This is a 1 megahertz 8-bit processor, right? What can it possibly do? What do you think?
There's this thing, we have a Bluetooth tracker.
Yep.
It has like a little processor that runs and it lasts for like a year and a half.
2 years.
2 years, something like that.
Yep. And that's because it can even go into power down mode. In other words, it's not active all the time. Because if I go back to the data sheet, you can see that it has several numbers in terms of power consumption. The full active mode, which means it's executing program, actually doing stuff, is 200 microamp, as a current draw. When it's idling, which means it is actually clocking, the internal oscillator is still running, but it's not actually executing anything, which usually means it is at a halt instruction. That's why the halt instruction actually has practical value in actual industrial programming, because when you execute the quote-unquote halt instruction, even though the clock is still ticking, it's not consuming as much current. In fact, you can see that the power consumption is only 1/8 compared to what it would when it's in active mode. So that means you're extending that 1 and 1.6 years by 7 times. So 1.6 times 8 is more than 10 years. Okay? And that's only when you go only into idle mode, but not in power down mode. Power down mode means it will turn off the clock. The clocking mechanism, which usually is either going by RC oscillator or ceramic or crystal oscillation circuit, it takes time for it to spin up again. In other words, if you go to power down mode and you want to go back up to active mode, it will take, if I remember correctly, in microseconds, okay, it usually takes less than a millisecond to get it back to the clock speed that it needs to run everything correctly. But if you can live with that, and you just say that, every minute I only need to be awake for 5 milliseconds, you can save a lot of power. Okay, and most alarm, devices, they don't need to sample all that frequently. Okay, like how many of you have installed those things at home? It's a Zigbee wireless battery type of thing. You can attach it to the window, door, so that when somebody opened the door, you have something that would trip. I'm surprised that mine is still running. I mean, after like 2 years, it is still on the original battery. And we are talking about one of those tiny CR123 type of batteries. It's still running on it. And that's because everything can go into power down mode, and then you can wake up four times per second, okay, which is enough to catch that the window has been opened, okay. You can wake up like 4 times per second, and then each time it wakes up, let's say it takes 100 milliseconds to execute. So that will still give you a lot of time to be in power down mode, and that's why you can extend the battery life like crazy, because we are looking at a ratio. Okay, let's go back to the spreadsheet. Where is it? Okay, so we are looking at power up amount of time. So let's say it is 1.1 seconds, okay? And we want to do this, is it 0.1 seconds? 100 milliseconds. Yeah, okay. But we want to do it every 1 second, which means the duty cycle is only 10%. So practically you're extending the battery life by 10 times. So that 1 year and 1.6 years is now extended to 16 years. Yep.
Does it take extra power to turn it on to power?
No, when you turn it back on again, it will only take the 25 or 200 microamp in this case. But it will ramp up too. So initially it's not going to consume 200 microamps. It's only when it get up to the full speed, then it will be running at 200 microamps. So what can these things go into? It's only 17 cents per part. It's really small. The packaging, I'm not going to talk about the packaging too much here, but if you look at the packaging, okay, let's see, does it talk about the packaging? Yep, packaging information. So it can come in this particular format, which is a fairly standardized format. It's got 6 pins, and these are all measured in millimeters. So we are looking at the overall dimension, which is E times D. So E is 2.6 millimeters and D is 2.8 millimeters. In other words, the entire chip, including the full extent of the pins, is less than 3 millimeter by 3 millimeter. And that's the larger of the packaging. That's the big one. That's the space wasting packaging. The other packaging I think is smaller. This one looks smaller to me, way smaller. So we are looking at D times E again, and this time we are looking at 2 millimeters by 2 millimeters. That is a tiny little package. How many of those do you think can fit on your thumbnail? Okay, I'm looking at my own thumb, which is not particularly big. It's about, I would say, across about maybe, I would call it 15 millimeters. So it's about 15 by 15. It will fit what? 49 of those chips on my thumbnail. So that means size-wise, it is miniature. Power-wise, it doesn't consume too much power, and also cost-wise, it doesn't cost much. But it is a full processor. You can write programs on it. Most of the time with these parts, you have to write it in assembly code because they don't have enough resources to run C code. But the question is, what do you think it can do? You can control all kinds of stuff. You can do a 3-phase motor control if you want to. You know, remember those brushless motors that everybody wants with their RC cars? This can do it. You can use it in an alarm situation. You can use it to monitor things like temperature. It can actually read analog value. In other words, it doesn't just say, it's hot, it's cold. It can actually tell you how hot it is, how cold it is. Okay? But you need a thermistor and some external components to do it. But you can write a significant amount of programming with these things to perform intelligent programming, to perform intelligent control tasks. And what about the job market for these things? Do you think we can put one of these things into a ranch? Why would I put one of these things into a ranch? Yep, exactly. I want to know how much torque is applied. Okay, and these things can do it. You just need a Bluetooth chipset to go with it, and then your phone can display how much torque is actually getting applied, or you can pre-program the torque range and say, if I get to this amount, you'll beep me, let me know that I'm in the right range, and when I'm right at the right value, you'll give me a long tone so that I know when to stop.
There's a little clicker, it's like mechanical.
Yeah, but we're trying to avoid mechanical stuff, right? Yeah, this is so much more reliable. What else can you do with this?
Could you measure your heart rate?
Yes, you can. But you will need LEDs and some feedback mechanism, so you need to have LEDs and a photodiode or phototransistor to read back how much light is either going through your finger or get dispersed back to the sensor. From that, and you sample it at a certain rate, yes, you can actually check your heart rate at least. They're already talking about blood pressure sensing on the casing of a phone. So when you're holding your phone, you're just doing your usual texting, your phone is actually taking your blood pressure. And these chips can do that. So think about all the things they can do with inexpensive chips that can last a long time, doesn't consume much power. If you think about all the possible applications, then you think about who's going to write all that program. Okay? I think most of you are thinking, okay, when I graduate, I'm going to work for Microsoft, I'm going to work for Google, I'm going to work for, well, I guess not Uber anymore, right? But those companies only have like flagship products, a certain number of products to maintain, okay, and they innovate in a very slow rate, at a slow rate. But when you think about, with processors like this, what kind of applications they can get into, and how many applications that they can get into, and how fast these things can change, there's a lot of possibility. Is that making any sense? So I think some of you may be looking into this, like when you're about to graduate. But I think this is a direction that some of you can definitely look into. If this interests you, I think there are a lot of possibilities. Is that okay? So one last thing, I know it's time to get out of here. In 1990, which is really not that far long ago, right? It's only about, what, close to 30 years ago, okay? So close to 30 years ago, what we can do with a 2mm by 2mm chip requires a circuit board about this big. And that has a power consumption of close to 200 milliamps. This is 200 microamps. In other words, 1,000-fold of power consumption difference. Okay? And this has more processing power. It has more devices that are built into the device itself. And we used to make, the company that I used to work for, sell these circuit boards for about $300 to $400 each. And now it is 17 cents. And that's only 30 years. You might say, Tech, you're an old man because you're talking about stuff from 30 years ago, but 30 years is not that long, okay? And by the time you graduate, which is another, 2-3 years at least, right? Things will be even less expensive or more powerful for the same price. So you kind of have to keep that in mind, the trajectory of technology, so that you can be ready for that when you graduate. All right, so enough lecturing from me, and we'll go to the lab.